okay? If you can draw the graph and your pencil never lifts to draw it, it's continuous. I never lifted my pencil to draw that. Correct. That's discontinuous because I had to lift up my pencil to get to the other place. You saw a couple of graphs that had like a hole in them like that. I had to lift my pencil to leave that hole out. It's discontinuous. Okay. So if you have to lift your pencil to draw it, it's not continuous. It's discontinuous. Or it has a discontinuity in it. Okay, that's what we call it, is a discontinuity. If there are no holes or breaks in the graph. If there are, I guess, breaks or holes, if I'd read the second one, I would have known what went in those blanks. It is considered to be discontinuous. Now, we have different types of discontinuities, and you have the three of them that we will be working with here listed down below. The first one, I don't know why you don't have a place to write it, but the first one has asymptotes, right? We know that that's one we've been talking about, this type of graph. It has like an asymptote here and an asymptote here. Definitely not continuous. I had to lift up my pencil to draw both pieces. This is what we call an infinite discontinuity. Do it? Do it? Does it? Oh, okay. I couldn't see it. Okay. So yes, that's an infinite discontinuity. So if it has an asymptote, that causes it not to be continuous. Now, if it just had one piece with an asymptote, like think growth or decay, right? Growth or decay looks like this. This is still continuous. Even though there's an asymptote here, it's still continuous. I didn't have to lift my pencil. It's whenever I move into two pieces that it becomes an infinite discontinuity. Do you see the difference? Am I talking too fast? Okay. Yep. That's the type of discontinuity, yes. That's okay. That's all right. All right, the second type of discontinuity that we will deal a lot with looks this way. I have these two pieces. First of all, why are both of those not filled in? Why is one filled in and not the other? Then it won't be a function. It would fail a functionality test, right? If this was filled in, I'd have two y's for one x. Wouldn't be a function. But in this case, it is a function, and it is a discontinuous function, and the type of discontinuity, these are big words I know, and it sounds fancy, but it's really not, is exactly what it looks like. It is called a jump discontinuity. I literally draw a piece, stop, jump up to another piece and draw it. That's called a jump discontinuity. Then the very last one has a hole in it. And when we have holes, we call these removable discontinuities. If I could remove that just one point that's missing, or I could actually remove, I could make it be continuous. And what we'll do is we get later on in our career in pre-cal, I guess, I don't even know what I'm trying to say here. We'll talk about plugging that hole to make it continuous, but that's why we call it removable, because we remove it out to make sure that it meets all the criteria. Mr. Law is out there having a grand time. Yes, there could be. There could be. There could be. So looking down at the examples, yeah, number one, what type of discontinuity does that look like? Jump, that's a jump discontinuity. How about number two? That is continuous. The location is just where it happens, the x value. So like for number one, it is not continuous or has a discontinuity at x equals, what is that? -5. Because we'll be fixing some of the discontinuities at some point. So you have to know where they are. Kinda, yeah. Plug in only holes. We'll plug holes. That's about it. You only have to do the x. We describe it with just the x. 2 is continuous, so all you have to do is write continuous. How about 3? Not continuous, what's the type? It's an infinite discontinuity. Where does the discontinuity occur? The asymptote. So where's that vertical asymptote? At 1. So it's discontinuous at x equals 1. Number 4, continuous or nah? Continuous. Why is it continuous? I don't have to pick up my pencil. That's the most basic definition. How about 5? A removable discontinuity or a hole. Yep, because it's a hole. At -2. Yep. Where's the hole? What x value is the hole occurring? Is it 3? 1. Oh, at 3. Yeah, sorry, 3. And number 6 has 2. That's exactly right. It's discontinuous, and the discontinuity occurs 2 different places. I have an infinite discontinuity at x equals what? 2. I know, it's hard to tell. I have an infinite discontinuity at x equals 2, and I have a removable discontinuity at x equals 4. It sounds worse than what it is, right? If I just walked in and said, where's the removable discontinuity, or where's the, it sounds pretty advanced, but it's not hard. Yeah, it's hard.
It's because there was a darker line. Yeah. So it's still an infinite. There's just like things.
Yes, so both of them. Yep. Did you have a question, Kaylee? 3 lines on which one?
No, there's really the asymptote. I thought it was the graph.
Just the asymptote, yeah. All right, let's put, remember, this is just the classwork. You don't have to, oh, you're on the homework. No. Yes, in behavior. So remember in behavior, if you have forgotten, and this is getting us, we're going to start doing limit, I don't know if you guys remember limit notation from Algebra 2. I feel like we touched on it, but if we didn't, we will be getting ready to do limit notation. But here, what we want to do is, in behavior describes the 2 ends of the graphs, or the 2 ends of the graph, assuming there's only 2 ends of the graph. But here we do the right side as x approaches infinity. So that says the right end of the graph. What does the graph itself do? Does it go up or down? It goes down, so that would be negative infinity. And then as I look at the left side of the graph, so that's as x approaches negative infinity. Y'all remember doing this? Then f of x approaches, well, it's going up, so that would be positive infinity. But when I get into some more advanced graphs that have asymptotes and whatnot, like if you go on down past number 9, you name me, Aaron. Am I going too fast? I'm sorry. So this says the right end, which is this end, is going down.
Oh.
And then this says the left end is going up.
Yeah. Is there a shorter way like that?
Well, we'll do limit notation soon, but no, not right, not just yet. It doesn't matter because you're only looking at the ends. That's it, just the ends. Getting us ready for some nice curve sketching. Now, sometimes the ends don't go up or down. Sometimes they go towards a certain value, like on the example that's on here. It looks like I have an asymptote at -1, so it does something like this and like this, right? So now as x approaches negative infinity, so the left side, I think your paper does positive infinity first, it doesn't matter. The left side, it's not going up or down. It's not approaching an infinity anymore. What's it approaching? It's getting closer and closer to what value? -1. The y value is getting closer and closer to -1, right? Because it's approaching this asymptote. And then on the other side, same thing as x approaches infinity. So now as I look at the right, it's not going up or down forever, right? It's getting closer and closer and closer to this value. So f of x is approaching -1 from both sides. Yes. And we will learn soon that is literally the definition of an asymptote. A horizontal one anyway. So this is the left end. For the second line, yes. Why can't I? There we go. So then whenever I got to this side, this is the right and this is the right. Yep. Yes. Yes. Negative infinity. On 9? Because it's still going. So you got this graph that's doing this. Something crazy like, oh, this is kind of doing this. So the right end is still going up and the left end is still going down. It's not getting closer and closer to a number. To get close to a number, we're looking at a horizontal asymptote. Yes, there's only one asymptote. That's like a growth one. I know.
You said the whole thing?
Yes, second page homework. 1 through 18. It shouldn't take you long. Homework or classwork? 1 through 18.